This video will introduce you to the binomial expansion. We will develop a formula to find the terms of the expansion of a plus b raised to the power of n, where n is any positive integer. This is called a binomial expansion because the original expression has two parts. We know that a plus b squared equals a plus b times a plus b, which expands to, quote, a squared plus 2ab plus b squared. We can write this as 1a squared plus 2ab plus 1b squared. Thus, the coefficients are 1, 2, and 1. Next, let's look at a plus b cubed. This is a plus b times a plus b squared, which equals a plus b times a squared plus 2ab plus b squared. Multiplying this out gives 1a cubed plus 2a squared b plus 1a squared. We continue the expansion by multiplying the quote term by a squared plus 2ab plus b squared. This gives us plus 1a squared b plus 2ab squared plus 1b cubed. Now we add the terms together. 1a cubed remains the same. 2a squared b plus 1a squared b equals 3a squared b. 1ab squared plus 2ab squared equals 3ab squared. Finally, 1b cubed remains the same. So the coefficients of the expansion of a plus b cubed are 1, 3, 3, and 1. Let's expand a plus b to the power of 4. It's a plus b times a plus b cubed. This equals a plus b times 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. Multiplying this out yields the coefficients 1, 4, 6, 4, and 1. For the expansion of a plus b to the power of 4, the second coefficient, 4, is found by adding the coefficients 3 and 1 from the previous expansion, a plus b cubed. Similarly, the third coefficient, 6, is found by adding the coefficients 3 and 3 from the row above. This pattern shows a systematic way to find the coefficients. Here is a summary of the coefficients for the powers of a plus b up to the fourth power. Note the triangular arrangement of the numbers. Each number in a row can be found by adding the two coefficients directly above it. This structure helps predict the coefficients for higher powers. Observe the pattern. The first and last numbers in every row are always 1. To complete the coefficient triangle, we can fill in the obvious ones at the top. For a plus b to the power of 0, the coefficient is 1. For a plus b to the power of 1, the coefficients are 1 and 1. This pattern of binomial coefficients is known as Pascal's triangle. Note that the nth row gives the coefficients of a plus b to the power of n minus 1. However, it's easy to know which row we want, as the second coefficient always matches the power. For example, 1, 3 for the third power, and 1, 10 for the 10th power. Let's find the coefficients in the expansion of a plus b to the power of 6. Since the power is 6, we need 7 rows in Pascal's triangle. Starting with 1, the coefficients are 1, 6, 15, 20, 15, 6, and 1. We often need the complete expansion, not just the coefficients. For example, to find the expansion of a plus b to the power of 5, Pascal's triangle gives the coefficients 1, 5, 10, 10, 5, and 1. The full expansion is written by combining these coefficients with the powers of a and b. A useful tip: the sum of the powers in each term equals 5. Now, let's write out the expansion of 1 minus x to the power of 4 in ascending powers of x. Ascending powers mean the first term has the lowest power of x, and the powers increase. The coefficients for a power of 4 are 1, 4, 6, 4, and 1. We know the expansion for a plus b to the power of 4. To get to our problem, we need to replace a by 1 and b by minus x. Substituting these values, we get this expression. Remember, the brackets around minus x are vital, especially when squaring the minus sign along with x. Since we know that any power of 1 is 1, we could have simplified the previous expression by omitting the ones for a in the binomial expansion, like this. Simplifying the powers of minus x in the full expression gives the final expanded form of 1 minus x to the power of 4. Alternatively, we could go straight to the simplified form by recognizing that the powers of a, which is 1, will not change the term's value, simplifying the initial substitution step. Let's work through an exercise. Find the expansion of, quote, 1 plus 2x to the power of 5 in ascending powers of x. The coefficients are 1, 5, 10, 10, 5, and 1. Using the coefficients and substituting a equals 1 and b equals 2x, we get the following expansion. Notice how the powers of a are 1 at every step. Simplifying the powers of 2x and multiplying the coefficients gives the final expanded form. 1 plus 10x plus 40x squared plus 80x cubed plus 80x to the power of 4 plus 32x to the power of 5. If we want the first few terms of the expansion of, for example, a plus b to the power of 20, Pascal's triangle becomes impractical due to its size. We can find each coefficient by multiplying the previous one by a simple fractional sequence. For a power of 6, the fractions are 6 over 1, 5 over 2, 4 over 3, 3 over 4, 2 over 5, and 1 over 6. To find the ninth coefficient of a plus b to the power of 20, we would need 8 fractions. This is tedious, so we use a shorthand notation called the binomial coefficient, represented as 20 choose 8. The binomial expansion of a plus b to the power of n is given by the terms shown here. We know the first two coefficients are 1 and n from Pascal's triangle. To complete the pattern, we can write these coefficients using the C notation. N choose 0 is 1, and n choose 1 is n. Since n choose 0 is calculated by, quote, factorial divided by 0 factorial times n factorial, 0 factorial must be equal to 1. Any term of a plus b to the power of n can be written as n choose r times a to the power of n minus r times b to the power of r. Here, r is any integer from 0 to n. A useful tip. When finding binomial expansions, the powers in each term always sum to n. For instance, n choose r is equal to n choose n minus r. Therefore, the coefficients are symmetrical. For example, n choose 0 equals n choose n choose 1 equals n choose n minus 1, and so on. Let's look at some generalizations. The binomial expansion of 1 plus x to the power of n in ascending powers of x is given by this formula. Remember that r is any integer from 0 to n. The r plus 1 term is given by the formula shown. For the expansion of a plus x to the power of n, the generalized formula is also provided. Let's work through an example. Find the first 4 terms in the expansion of 2 plus 3x to the power of 5 in ascending powers of x. The formula for the expansion of a plus b to the power of n is given. We substitute a equals 2, b equals 3x, and n equals 5. The required coefficients are found using the binomial coefficient notation. The expansion is then calculated by multiplying the terms, giving the final result of the first 4 terms. Next example, find the 5th term of the expansion of, quote, 2 minus x to the power of 9 in ascending powers of x. The 5th term is the r plus 1 term, where r equals 4. The term is calculated using the formula with n equals 9, r equals 4, a equals 2, and b equals minus x. Notice that the powers 5 and 4 are always the same as the numbers in the binomial coefficient at the bottom. Here is a summary of the binomial expansions. The binomial expansion of 1 plus x to the power of n and the general r plus 1 term are given. Also included is the general formula for the expansion of a plus x to the power of n and the related r plus 1 term. Let's try some exercises. First, find the first 4 terms of the expansion of 1 plus 4x to the power of 8 in ascending powers of x. The solution is provided.